So welcome back all. By this session, we begin our next module. We begin with the concept of directional derivatives. We have seen the derivative of a vector function, and let's encounter how does it differ from directional derivative and what do we mean by directional derivative. So let's consider a scenario where we have a function of two variables, say f of xy. It is defined throughout a region R. The function f of xy is defined throughout a region R, so it's just a region R. So obviously this region R has to be on the plane since we need two variables to define the function f. Right, so everything coming from R has to be an ordered pair, and for that reason R has to be a part of a plane. Right. Suppose u equal to u1i plus u2j be a unit vector. So u equal to u1i plus u2j is a unit vector. You are much familiar with unit vectors. Unit vectors are those vectors having the magnitude 1. Right. Let p naught given by x naught, y naught, z naught be a point on the space. Right. So what are the things we do now have? F to be a function of two variables which is defined throughout on a region R over the plane. U given as u1i plus u2j is a unit vector, and p naught given by the coordinates x naught, y naught, z naught is a given point in the plane. Right. If so, the parametric representations of the straight line passing through p naught. Remember, the parametric representations of the straight line passing through the line p naught in the direction u. In the direction u is given by x equal to x naught plus su1 and y equal to y naught plus su2. This is how we have expressed parametric equations. In our previous sessions, we haven't written explicitly x equal to something and y equal to something. Instead, we have given another notation like x naught plus su1 comma y naught plus su2, and this obviously serve in the places of x and y in a Cartesian coordinate system, and for that reason we can sometimes explicit these parametric equations in this form. Right. So this is no way different from our previous experience of parametric equations. So at this point we think about the directional derivative. So remember our previous setup, we had a function of two variables. We had a unit vector u which was actually given as u equal to u1i plus u2j, and we had a point on the space p naught which was given as x naught, y naught and z naught. This was the initial setup we have. Now, derivatives were always about rates of change. We have seen that. We encounter a special kind of derivative here. Think about the rate of change of f at p naught in the direction of u. Right. So there are certain subtleties here to be examined. How does the graph of f of xy look like? Will it suffice to embed the graph in a plane? No way, since we have two variables here and the function value has to be another real number. That will need another axis, which in turn give us a spatial system to represent the graph of f of xy. So it makes sense to think about the derivative at a point in the plane, in the space. And obviously, since all the points are coming from a plane, and this vector lying on the same plane, it makes sense for us to examine the derivative or the rate of change of f in the direction of this vector. Right. Don't get confused about these things. We'll be clarifying it sooner. Right. So what we need to think about is the rate of change of f in the direction of u at p naught. So let's move to the definition directly. The rate of change of f df by ds in the direction of u at p naught. Remember this s, which comes from the previous definition or previous parametric expression for the straight line passing through p naught and parallel to the vector u. Right. It actually gives the arc length thing. We have seen that. So df by ds at u p naught is given as a limit s tends to 0, f of x naught plus s u1 comma y naught plus s u2 minus f of x naught y naught whole divided by s. This actually resembles our previous definitions of limits, which we have expressed as previous expressions for derivatives, which were actually fundamentally expressed as limits. Right. So this actually gives the formal definition for the rate of change of f in the direction of given unit vector u at p naught. This is called the directional derivative of f in the direction of u at p naught. Right. The directional derivative of f in the direction of u at p naught. Remember, this limit need not be always existing. Right. So the directional derivative is defined if and only if this limit exists. Remember, this is very much important, which gives us an idea that the directional derivative of a function need not exist always. It is not necessary that the directional derivative of a function to exist in all the directions. Right. It may exist in some directions, it may not exist in others. Right. As we have seen for normal derivatives, we had a cumbersome definition like this, but we haven't used it. We had certain other techniques to find the derivatives of a function. Right. In the same way, we have certain techniques to find the directional derivative of a function in any direction at any point. Let's examine that now. So one such idea to find the directional derivative of any function comes from the concept of gradients. Right. So what are gradients? Gradient. Consider we have a function f of xy. See, we are actually explaining all these concepts for functions of two variables. As I repeat certain times, everything we discuss here is applicable for any finite number of variables, any function of any finite number of variables. Right, so this can be easily extended to three-dimensional system or functions of three variables or anything. Right, so consider we have a function f of xy, whatever it is. The gradient of f denoted as this may be called as grad f. Right, so the gradient of f denoted as grad f is nothing but dou f by dou x I plus dou f by dou y j. So this was originally a scalar function and we have generated a vector out of it. So gradient of f is a vector function, evolved from the scalar function f, which is explained as or expressed as grad f equal to dou f by dou x I plus dou f by dou y j. Right. Now let's connect this with directional derivative with a theorem. Right. So the theorem is if the partial derivatives of f is defined at P naught. Remember, P naught is given as x naught, y naught, z naught in the space. Given is defined at P naught. Then the directional derivative of f in the direction of u at P naught. Remember this u and P naught, everything as we have seen before, is also given as grad f evaluated at P naught dot u. Right. So what is this? What do we mean by this? We have seen the expression for directional derivative as a limit, and this particular equation expresses directional derivative as a dot product of two vectors. We have seen what is gradient. Gradient was actually a vector function evolved from the scalar function f as grad f equal to dou f by dou xi plus dou f by dou yj, and u is given, u is the unit vector given, and their dot product will give the required directional derivative. So this is the fundamental theorem we will be using to find the directional derivative of any function in any direction if they exist. Right. This theorem needs to be proved. So let's see the proof. So consider the line x equal to x naught plus s u1, y equal to y naught plus s u2. Remember, this u1 and u2 are coming from the unit vector u1i plus u2j, and x naught, y naught are coming from p naught, which was actually given as x naught, y naught, z naught. These are not just random numbers or random constants. Right. So this s is actually the arc length parameter, and these equations give us the straight line passing through P naught parallel to u. Right. Then df by ds in the direction of u at P naught is, we use the chain rule here. We had prior to using the chain rule, remember the expression, we had the function f of xy, and x and y are now functions of what? S, right? X and y are now functions of s. So using chain rule, df by ds in the direction of u at P naught can be expressed as dou f by dou x into dx by ds plus dou f by dou y into df dy by ds. Right. Since we have f as a function of x and y, and x, y are functions of s, and remember we are evaluating all these as the point P naught. These two quantities are evaluated at P naught. Right. Since we need to find the directional derivative at the point P naught. Now we have x equal to x naught plus su1 and y equal to y naught plus su2. So let's try to rewrite this. So I am not again writing that we are evaluating it at P naught. Remember that we evaluate these two quantities dou f by dou x and dou f by dou y at P naught. So what is dx by ds? X is given as x naught plus su1, where x naught is a constant coming from the coordinates for P naught. Right, so dx by ds is nothing but u1 plus dou f by dou y into dy by ds is u2 in the similar sense. Right. Now let it be there. What was grad f? Grad f was dou f by dou y I plus dou f by dou xi plus dou f by dou y j, and u was u1i plus u2j. Now find the dot product. go to the dot product, which is grad of dot u is our normal sense of dot product, dou f by dou x into u1 plus dou f by dou y into u2, which is interestingly coinciding with our expression here. So both of these are equal. From that we can conclude that the directional derivative of f in the direction of u at p naught is the dot product of gradient and the given unit vector u. Right. So this is how we practically evaluate the directional derivative of a function at any point in the given, in the direction of given unit vector. Right. So we can see an example now. Things will be much more clear when we move to examples. So find the derivative of f of xy equal to x e raised to y plus cos xy. Let me rewrite this. X e raised to y plus cos xy at the point 2, 0, at the point 2, 0, in the direction of the vector a given as 3i minus 4j. So this completes the question. We need to find the rate of change of f in the direction of a at 2, 0. Right, 2, 0 is obviously a point in the space. Right. So we need to find the directional derivative of f at given vector. See, we have a subtlety here to be mentioned. All the previous theorems were actually explained for a unit vector. The direction was actually given by a unit vector, but a here need not be a unit vector. This is actually not a unit vector. So we need to find a unit vector out of this. A unit vector which is in the same direction of a, which can be easily evaluated as a by mod a. Right. This is how we usually find the unit vector in the direction of any given vector. Right. So what is mod a here? Mod a is root of 3 square plus 4 square, which is nothing but 5. Right. So clear this off. So the unit vector in the direction of a, let's use the same term as we have seen. U is 3 by 5 I minus 4 by 5 j. Right. So now what is the directional derivative of f in the direction of u at the point p naught? Let's use the recent definition using dot product, which is actually grad of dot u. So what is grad f? So we need to find dou f by dou x and dou f by dou y. So I'll just write the unit vector here, 3 by 5i plus minus 4 by 5j, and for now I'll just clear this off. So what is dou f by dou x? So dou f by dou x has to be evaluated as at our given point 2, 0. So dou f by dou x is, so here e raised to y is a constant, e raised to y plus cos xy will be sin xy into y. Right. So sorry, it will be negative, since the derivative of cos x is minus sin x. So when we evaluate dou f by dou x at 2, 0, this is e raised to 0 minus sin 0 into 0, which is 1, e raised to 0 is 1 and this whole quantity reaches to 1. So this is 1. And similarly, what is dou f by dou y at 2, 0, which is e raised to y has the derivative with respect to y as e raised to y itself. So x is a constant. So the derivative with respect to y for x e raised to y is x e raised to y plus minus sine xy into x. Right. At 2, 0, this will be 2 into e raised to 0 minus sine of 0 into 2. This is e raised to 0 is 1 and this whole quantity sine 0 is 0. So this will be 2. Right. So we got dou f by dou x as 1 and dou f by dou y as 2. So from this information, we compress this to write dou grad f as 1i plus 2j. Right. Since grad f was defined as dou f by dou x I plus dou f by dou y j. So now we can find the directional derivative of f at u in the direction of p naught. P naught is 2, 0 here as grad f dot u, which is 1i plus 2j dot u is 3 by 5i plus minus 4 by 5j. Right. So what is the dot product here? 3 by 5 minus 8 by 5, which is minus 5 by 5 minus 5 by 5, which is minus 1. Right. So the directional derivative of the given function f of xy equal to x e raised to y plus cos xy at the given point 2, 0 in the direction of the given vector a is minus 1. Or a is fine. A, p naught is minus 1. Remember, a and u were of the same direction since the unit vector u was obtained from a by just dividing the whole vector a by its magnitude. So the required directional derivative has the value minus 1 at p naught. Right. So this is how we typically evaluate the directional derivative of a function in the direction of any given point, in the direction of any given vector at any given point.